For those that have just joined here, this is the Dispersants Herders webinar series that ExxonMobil is putting on, and we're going to start in a couple minutes because I still see a number of the participant numbers growing still, so we'll probably start a couple minutes after the hour, so hold tight. Let's give it another minute or so. It's populating fast right now, actually.
Wow.
So why don't we get started? Why don't we get started? So good morning to everybody in, I guess, the United States, and good afternoon or good evening to everybody outside of the United States. So my name is Tim Nedwed. I work for ExxonMobil, and I lead the oil spill response research program for ExxonMobil. And you are here to listen to the Dispersants and Herder webinar series, right? So we are planning to have we're having 10 weeks of webinars and various speakers. 9 of those weeks will be dedicated to kind of dispersant related issues, and 1 week will be related to herder work. So look forward to that. Today we're going to talk about dispersants, and we have a couple of very interesting speakers. We have 3 talks. We're going to move the order around a little bit based on what was in the agenda. Tom Coolbaugh is going to speak first, and then Dagmar Etkin will speak, and then I'll speak. So Tom's going to speak about some of kind of the basics of dispersants and how they're used and applied. So everybody kind of comes up to speed if you may not be that familiar with dispersants. And then Dagmar is going to talk about something completely different. Dagmar Etkin is going to talk about something completely different, the challenges with mechanical recovery, right? And I think, and the reason she's talking second is because it's important to put that into perspective, that for the type of spills where we think dispersants are important, which are large offshore oil spills, Based on historic data from spills, mechanical recovery is quite challenged, and Dagmar will go into the details of that. And then the last talk will be by me, and I'm going to describe some of the issues related to trying to represent fate and effect studies and dispersant effectiveness testing in a closed system, in a beaker in a lab, or even in a large wave basin like OMSET. So why are we having this webinar series? The reason is we've had a workshop at OMSET for the last several years, right? ExxonMobil has sponsored it a couple of years, and then API has sponsored it a year or two before that. The reason we did that is because it's important for us from the oil industry, because we advocate for all oil spill response tools in the toolbox, and dispersants are an important tool from industry's perspective for large offshore oil spills where other response options become quite challenged. We had the workshop at OMSET because it's quite convenient. They have a very large classroom for a workshop, but then you also were able to go out onto the tank and actually see a dispersant effectiveness test on the 200-meter long OMSET wave tank. So it was an ideal location to have both the in-class time and then the on-tank time. Unfortunately, the lockdown this year kept us from doing that. And so we decided to instead hold this webinar series, right? So there are advantages and disadvantages of that. The advantages is I see we have 156 participants, and the OMSET facility only allowed us to have at most 40 people. So we can't have the one-on-one kind of interaction that we had at OMSET, but we are able to communicate with more people and then have maybe a wider variety of speakers that can speak as well. So as I said, all tools in the toolbox are our goal here. I'm going to introduce Tom. Tom, you want to put up your slides?
Yep.
So we'll jump right into the first speaker. And Tom's going first. So as you bring up your slides, I'll introduce you. Tom Coolbaugh recently retired from ExxonMobil after 34 years, I think.
32 and a half.
Is that right? 34?
32.
32 years. So Tom works for Applied Research Associates for the last, what, 5 weeks now?
A month, yeah.
Applied Research Associates is actually the management team for the OMSET facility. So Tom is the program facility manager for the OMSET wave tank in Leonardo, New Jersey right now. His career has spanned, as he said, over 30 years. His focus is on the subject of science and regulatory aspects of the use of dispersants during oil spill response. He's a member of the National Academies of Science, Engineering, and Medicine's committee that prepared the report on dispersants called Responding to Oil Spills in the U.S. Well, two different reports. One is Responding to Oil Spills in the U.S. Arctic Marine Environment, and the other is the more recent one, the Evaluation of the Use of Chemical Dispersants in Oil Spill Response. So Tom is a chemist. He received his BA in chemistry from Amherst. He didn't tell me how long ago that was, so maybe you know. And he has a PhD in chemistry from Caltech, and he also obtained an MS in Management of Technology from NYU. So, with that, Tom, I'll let you jump into your slides.
All right. Here, I just wanted to start a timer just so I can.
Are you sharing your screen right now?
Yeah, I thought I was. Oh, there you go. All right.
Yeah, there you go.
All right. Yeah, so thank you very much. It's certainly a pleasure to be here. It is too bad that we weren't able to do the class here back in June. I would have been here as an ExxonMobil employee, but no, it's a wonderful facility, and hopefully we will be here in the future. So if people have a chance to come to OMSET, I certainly recommend it because you get to actually see what things look like when the oil's on the water. But I'm just going to go through. It's a fairly high-level overview of what dispersants are, what they aren't, why we would use them, why we wouldn't use them, and just a couple of misunderstandings that people have about them that Tim and I and others have spent a lot of time trying to at least increase the awareness and the understanding. So, without further ado, let's see if I can get this to go down. Okay. Yeah, we're getting there. Okay.
Hey Tom, while you're doing that, I forgot to mention something. So the way we're going to handle this is we're going to let Tom and Dagmar and myself speak first, and then have a time for about hopefully 10 minutes worth of questions. And the way we're going to ask questions is there's a Q&A button in Zoom, So go to the Q&A button and type in your question, and we'll collect those as the talks go. And then I'll read them out to the speakers and get through as many as we can before we need to go on to the next speaker. So be sure you go to the Q&A button. Everyone should have access to it, I hope, and ask your questions that way to avoid kind of too many people talking at once. Okay, sorry, Tom, go ahead.
And so hopefully you've seen the next slide. I hope that came up. So as Tim mentioned, there is a toolbox of oil spill response techniques, of which the best, if we can, certainly if you don't have a spill, that's the best thing. But if you do spill something, if we can pick it up and put it back, that would be the next best. But in reality, especially in the open ocean, that's a very difficult thing to do. Most spills are small. They tend to be closer to shore, and actually mechanical containment and recovery is really the preferred choice. But at least when it is in the open ocean, the focus that we have has been the use of dispersants, because we'll talk about why. But they can be delivered by air, by vessel, or in the case of Deepwater Horizon, Macondo spill, we learned that subsea works as well. So we'll talk about that. The key thing is, though, to be able to get to the oil and do something with it. So there's something that we talk about that's called encounter rate. And there's a quote there from Al Allen, who's been involved in oil spill response for quite a while. But if you can't get to the oil with either your personnel or your equipment, it doesn't matter what you have, because you're just not going to be able to deal with it. So the ability to get out there and do something effectively is really the key, and it's the challenge. And we just show this picture. This was a snapshot of what the water surface looked like around the Macondo spill back in 2010. And it's just to give you a scale. There's a boat, that yellow arrow, a couple of 100 feet, moving probably it's 4 or 5 knots. And that's just moving through the water. Now, if you imagine you're using a skimmer trying to collect oil on that kind of a scale, it's a rather daunting thing to try to do in what we call an operational period. And that was coming up every day. So the scale of the problem can be pretty big, and that's where we have to understand what the tools are. The main thing is to understand that oil on water is not static. Just by itself, it will spread, it will thin, but at the same time, you have winds and currents that are moving in different directions as well. So it doesn't stay homogeneous, it doesn't stay thick, it becomes more and more of a challenge the longer we wait to do something. And that's a matter of minutes that you start to see slicks spread fairly quickly. Now, let me just double check. Can people hear me okay? Because the last time I gave a talk, it was scratchy. Okay, seems all right? Good.
Yeah, no, it's great.
All right. So the main thing is to use all of the tools as effectively as possible. And unfortunately, in large-scale spills over a long period of time, you have plenty of time to do that. But the goal is to do things safely. So human safety is paramount, so responder in public. But then get the equipment out there, look for the thickest oil, get to it as quickly as you can. Mechanical recovery, if you can find thick oil, that's fine. But don't wait to start thinking about what the other options are. So if dispersants are an option, start thinking about them early on, because sometimes if in a single release, we're just talking about a matter of hours to a couple of days. And if we haven't responded within that time frame, it doesn't matter at that point. Things have changed. But it's looking at what the priorities are. So certainly human life, but then looking at minimizing wildlife exposure. It talks about habitat contamination. Our goal is always to think about keeping it off of sensitive shorelines. In the case of the Macondo spill, most of the shoreline in the Gulf of Mexico is considered to be sensitive. So keep it off the shoreline. But around the world, we may find that other things are important too, such as beaches, marinas, shoreline property. But we need to understand what the environment in which the oil spill is to at least make the optimal response. So it's a matter of using all the tools in the toolbox as effectively as you can. The goal, though, for dispersants is to take it off of the water surface, where if you leave it, it will eventually find its way to a shoreline. If we can disperse it into the water column as small droplets, there are microorganisms present essentially everywhere, many of which that can actually degrade oil. And the goal is to use this energy source as something that can then be degraded by the population, the microbial community that's there. And I show here, these are pictures that I thank Tim for preparing over the, I don't know how many years ago this was, but they're really good. And whether it's surface application or subsea, it's the same story. It's a matter of making very small droplets that stay in the water rather than floating up to the surface in the case of the subsea release, or staying floating on the surface in the case of a surface release. The goal is to make very small droplets that then get colonized reasonably quickly by the microbial community that exists. And we've seen that there are a lot of places where there are natural oil seeps and the microbes are already there. And they can expand, colonize, and then degrade the oil in a matter of days to weeks. What are dispersants? It's a solution of a surface active component, surfactant, that a lot of you will have run into, whether it's in dish detergents or other things. It's that same type of capability of cleaning oily, greasy things, because it's divided. The chemicals that we work with have a hydrophilic and a lipophilic end to it. So one likes the water, one likes the oil and grease, and they just align themselves at that oil-water interface, and they help reduce the surface tension, so that by applying minimal energy, typically through waves or other type of action, it makes very small droplets on the order of 50 microns, which is about the width of a human hair. And the whole point with using dispersants is to do it in an area where there's a large capability for dilution, because we are putting oil into the water, which by itself it's a toxic component, but we want to minimize the exposure of whatever might be in that water where we dispersed it. So that's part of the requirements. You need a minimal depth and hopefully a minimal distance away from shore, but the whole point is to have a place where you can dilute it fairly effectively so droplets don't find themselves again, they don't recoalesce. And it's maybe 10 to 100 parts per million, and essentially at the beginning, but within hours, we're down in the single digit, and then subparts per million by hours to days. So as I mentioned, the hydrocarbon is a good energy source for a number of bacteria that can degrade them. And there's a concern sometimes about nutrient limits or oxygen limits in the water. If you suck up all of the oxygen, then it becomes a toxic environment for organisms that need the oxygen. But because of the ability to dilute, we'll see the dilution down to levels where the microbes can degrade it without depleting nutrients or oxygen. And we've seen that during the measurements that were done during the Deepwater Horizon response. Just a schematic, again, just in that top 30 feet or so, 10 meters, it's been measured up to maybe a couple hundred parts per million, but within hours down to a part per million. The main thing to at least understand is that the exposure is generally below any toxic thresholds for those organisms. And there are a lot of standard, there are some standard toxicology tests that are typically done in a fixed volume at a fixed concentration. And the whole point is to raise up the concentration until you see negative effects on whatever the test species are, whether it's a fish, whether it's a shrimp. So you will hear concentrations that are called either the lethal dose or the lethal concentration, where toxicologists look at killing 50% of the test organism. So it'll be an LC50 or an LD50. But in reality, in the open ocean, we don't see those concentrations because it's sort of a spiked exposure where there will be an increase, but then because of dilution and degradation, it will drop down fairly rapidly. But standard tests are certainly something that has to be done. But as it says there was a National Academy study back in 1989. Again, concentrations start low, but then they dilute even further. There's also concern about what are dispersants made out of. Are they toxic? And in reality, most everything has some toxicity associated with it. But the formulation for, in this case, it was called Corexit 9500, which was the primary dispersant that was used during the Macondo spill response. It was designed to actually use components, these surfactant components that have low toxicity. And Nalco, which is the manufacturer, ultimately did release the components, the chemistry that was in there, and that's what's on the right of this slide. So what you see, span, tween, and aerosol, those are the surfactants. The glycol butyl ether and the isopar solvent, those are the solvents that carry it. But the main thing is to see that these are materials that through experience are in common day-to-day products that probably everybody on this call has probably been exposed to over the last day or so, whether it's a skin cream, shampoo, face lotion, it's a common material. And these were actually formulated because they were on a Food and Drug Administration list of low toxicity surfactants. So they were designed with safety in mind. Just a study that was done a while back by Environment Canada, looking at some common household dish soaps in this case, and looking at them compared to the two commercial dispersants, Corexit 9527 and 9500. In this case, a lower number means it's more toxic. So it takes less to hit that, in this case, lethal concentration that kills 50% of the pest species. So if you look at Corexit 9500, it's actually more than 20 times less toxic than the stuff we use to wash our dishes with. So again, the concern shouldn't be about the dispersant, but really it's the toxicity of the crude oil that we're dispersing into the water column, because that actually does have a higher toxicity. Plus it will be in there in a higher concentration, because typically we use 1 part of dispersant for 20 parts of oil in a sort of the initial go-in position for dispersing oil. So 5% of the loading of the oil. So it's a less toxic, less material. Subsea dispersant injection, so I showed that. Tim is very familiar with subsea dispersant injection. He's been the champion for this as a response technique since Deepwater Horizon. And it really can remove or prevent oil from coming to the water surface. So back in 2010, on May 9th and May 10th is when the EPA actually wanted to see proof of performance that the dispersants can work subsea to prevent exposure to surface organisms and spill responders. And this is just a few snapshots that were done from ocean imaging. In the upper left, that was before any subsea dispersant injection was used. That was a typical scene on a daily basis of the oil rising. In this case, the rig inside that yellow oval was, I think it was one of the rigs doing one of the relief wells, and it'll show up as a reference point in these other ones. So this is in 5,000 feet of water. The oil would take on the order of, let's say, 3 to 5 to 7 hours to come up, depending on the droplet size, because it does float. It's less dense than water. So over a period of hours, that oil would make its way to the surface and show up as a slick like that. On May 10th, when they started injecting subsea dispersant through a coiled tube down 5,000 feet, several hours after that first test, the picture on the upper right, it starts to look like there's less surface expression. That's the same rig as there. The bottom left is after 11 hours. And in conversations with the person who took these pictures, it really looked like the well had been capped, because there was that little oil showing up at the water surface. They stopped adding the oil, and after hours, the slick started to resurface. And based on that demonstration, the EPA agreed that subsea dispersant injection could be continued as an effective spill response tool. There are some challenges because we're adding chemicals to the environment to do something in a bad situation like an oil spill. The question is, what are we really doing? So there are some misunderstandings that are really influenced by people's inexperience with spill response, their fear of chemistry, the fear of the unknown, and sort of lack of trust for industry and maybe even government regulatory agencies. So one is this comment that dispersants are used simply to remove the oil from sight, to hide it. In reality, the dispersants do take it away from the water surface, but the goal is not to hide it. The goal is to put it into the water column as these small droplets that stay sort of neutrally buoyant, where again, they can be colonized by bacteria and actually be removed from the environment, because they will be degraded primarily to water and CO2. The stuff that's left behind is not bioavailable. It's more or less like an asphalt type material that has low toxicity because it's not available to the organisms. Another one is it's just a cheap alternative to other response techniques. In reality, we don't worry about cost. As an oil industry prior member, I'm not part of that anymore directly. The goal is to do things right. And you know, the fact that well, there are no cheap alternatives in an oil spill. Everything that's done has a fairly high cost, but it's even more costly to not do the right thing, to try to do an extended shoreline cleanup that may take months to years, as opposed to being able to do something with dispersants that you can do in hours to days to weeks, is much more effective and much more beneficial to the environment. And especially when you're dealing with a large scale offshore spill. The other one about adding dispersants is adding a toxic chemical to an already polluted sea. Yes, we are adding a chemical to it, but the toxicity of it is less, and the goal is, again, to dilute and disperse that oil where it has much less of a toxic effect on the organisms. If you think of a floating slick, by definition, that's pure oil. It's 1,000,000 parts per million. And if you happen to be an organism that's near it, there are some toxic components that are going into the water column. But if you happen to be a marine mammal or a bird, The challenge there is if you do get oiled, the after effects of that can be very severe. So again, we understand the not adding a chemical, but it's, again, low toxicity, and the goal is to have something that has high biodegradability, and it does not increase the toxicity of the oil. There was a Torrey Canyon spill back in 1967 that people will refer to and say, see, it was really bad, it killed all sorts of things, but it was not a dispersant that was used. It was actually an industrial degreaser that had high toxicity aromatic solvents associated with it. So industry has gotten much better over the years at really focusing on using non-toxic materials. The National Academies, as Tim mentioned, had a committee several years back. We worked on to look at the science of oil spill response and dispersants. The final version actually came out in 2020, so this is about as new as it gets. It used an awful lot of current literature that was developed since 2010. The goal was not to be an evaluation of the Deepwater Horizon spill, though. It was to look at what do dispersants do. And some of the key findings as are highlighted there is that dispersant application can be an effective spill response when used appropriately. They can decrease the volatile organic chemicals, especially for the response community who's on the surface trying to do something. If you can reduce the levels of those aromatic or other hydrocarbons that are in the air that could be health concerns, that's a benefit. Also, if we can reduce the areas that are oiled, keep it off the water surface, keep it off the shore, again, it can be beneficial. The one comment I like there is if dispersant use can shorten the duration of a spill, overall impacts to the community and others should be less, just because it's less time. Still, there's still ongoing work that's being done. There was a Gulf of Mexico research initiative that spent $500 million over the last 10 years. And there's a lot of research that came out of that. And we try to keep up with what the academic community has been doing. And the main thing is it's a very complex field, and there's still work that's ongoing. And with that, I've got like a minute or so left, and I just wanted to say thanks for listening. It's a topic that means a lot to me, and the studies that we do, I think, have been pretty supportive of dispersant use when done appropriately for especially these large-scale spills offshore where mechanical recovery may not be feasible for a number of reasons, whether it's through weather, distance, logistics, or other factors. So with that, I'll call it quits. So thank you for listening.
Tom, that's perfect. I have right at 20 minutes. I got to tell this story. Tom and I have given a lot of talks together, and one of the first times we gave a presentation about kind of oil spill response to internal managers, we had an hour on the agenda. Tom had a half hour, and I was supposed to have a half hour. Tom spoke for 55 minutes, and we then walked off, and as I was walking in, he looked at me and he said, "Good luck."
I don't know what you're talking about.
Yeah. Since you left ExxonMobil, you're getting better. The time for some reason. So, Tom, I think maybe we have some questions, and I think we have enough that maybe we can get through them. So I'm going to give another, 6 or 7 minutes for questions.
Okay.
And I'm just going to ask them to you. Some of them are pretty straightforward, I think, so you can be kind of pithy, and the others maybe you want to expound on. But the first question is, do you use cationic surfactants or anionic surfactants as dispersants?
Actually, they're strictly anionic and non-ionic. Cationic have higher toxicities, and they really aren't needed. Primarily the ones we have, there are 3 non-ionics and 1 anionic.
Great. So the second question is about the spill near Mauritius.
Yep.
And the question is, with regards to the recent spill near Mauritius, there have been commentaries that the effectiveness of current dispersants might be limited for the new low sulfur fuel oil. How true is that, and what would be the implication on dispersant use strategy? Okay.
That's a good question, because there are a number of oils over the years that we've looked at that aren't the traditional sort of Alaska North Slope crude that's relatively low viscosity and easy to disperse, whether it's a heavy fuel oil or, like you say, the low sulfur fuel oils. We're actually still focusing on what works, what doesn't. The challenge with some of those is they've got what's called a very high pour point that could make it a difficult thing to do anything with it, really. But there is actually work going on through the American Petroleum Institute and others to at least understand what the limitations might be. The biggest limitation we hear about over the years, the things we hear over the years, is viscosity limitation. If it gets above 10 to 20,000 centistokes, there are some who think it's no longer dispersible. But there's been work that shows that even in some of those heavier oils, they can still disperse. But it comes down to know your oil and understand what some of the characteristics might be. But if it's a waxy material or it solidifies, dispersion is kind of off the table. And Mauritius, I think that was a heavier oil. But still, if somebody could have gotten out there more quickly, the possibility could be that some of the shoreline impact could have been lessened.
Yeah. Hey, let me just add, the rule of thumb is, so pour point is the key issue, but the experiments show that if you're between 10 and 15 degrees C, so if the water temperature goes, or the oil temperature goes 10 or 15 degrees below the oil's pour point, this oil, if it was dispersible, is still likely dispersible. Oils are thixotropic, and so when they are in an energetic sea, just because you're below the pour point doesn't mean the oil has gelled, because it's getting shear stress from the movement of waves. So I would say we don't know for sure, but if dispersants are an option in a spill like for an oil like was in that vessel near Mauritius, then they should be attempted, right? You shouldn't just assume that it's not dispersible, because we don't know exactly what the conditions of that oil are after it's been on the ocean for a while. All right,
and we're also looking at having these sort of small test kits where you could actually do a test on site to get an idea.
Yeah, I'll describe that when I talk, but the recommendation is test the oil that you want to treat, right? Don't assume that some lab test that's done on a different oil at a different time is going to represent what happens in an actual spill. All right, next test is a simple one. Is toxicity tested on trouts? Is it only acute toxicity or long-term toxicity?
Well, these are typically done for 96 hours. So I guess you'd call that acute more than chronic, because some of the sub-lethal tests that have been done are really looking at even genetic changes and developmental issues. So these are pretty much just the acute tests.
Yeah, so our toxicologists say that Corexit 9500 is the product that has probably had more toxicity testing done on it than any other product in the entire world. The tests that Tom showed were acute toxicity tests, these 96-hour tests. But if you go to the literature, you can find all different types of organisms. More organisms have been tested, and you can see tests on both acute, chronic, and sublethal toxicity. What criteria have you evaluated when you formulate dispersants?
Wait, say what was the beginning of that?
What criteria do you use to formulate dispersants?
Okay, well, it's what's available, what chemistry is there, what has the lowest toxicity components. In fact, so Corexit 9500 was developed by an Exxon chemist decades ago. And again, he looked at what surfactants give what's called the HLB, the hydrophilic lipophilic balance, that gives you the best performance. But looking at them from a toxicity standpoint, he did pick things that through the FDA had low toxicity, but then you measure it with the effectiveness on standard oils, in this case maybe an Alaska North Slope crude or a Louisiana sweet crude, but just then to compare combinations and their overall effectiveness compared to one another. So using the same oil, vary the concentrations, the relative formulation, see which ones work best with the components that have the lowest toxicity. So it's a combination of toxicity and effectiveness balance.
Yeah, and 9500 has a big advantage because it's been tested over more oils, and I mean, industry spent probably millions of dollars testing Corexit 9500 over a broad range of oils.
And the challenge with coming up with a new dispersant is it's a product that you hope never gets used. So from a business model standpoint, it's kind of a challenge. I don't think I'd want to be in that business. Okay,
let's see. Let me get one that's kind of the science thing that you're on right now. Yeah, we'll hold that one off too. We have a talk about, there's a question about biodegradation, but we have a specific talk on that, so I'll hold that. How does their behavior differ in colder waters?
Well, there has been a lot of study. In fact, right here at the onset tank, they've done things in ice water. And if you look also at the Macondo, when it was being treated down at the wellhead itself, the temperature down there is about 4 or 5 degrees centigrade. And they work very well, whether it's at temperate waters, cold waters, they work perfectly fine from everything we've seen. There's been really no change based on temperature, at least for the modern formulations.
Yeah, again, the key is pour point. If you go more than 10 to 15 degrees below the pour point, oils that are dispersible in temperate conditions remain dispersible. If they get cold, unless you get too far below their pour point, is the kind of findings we've had over a long period of time.
Well, and the example there is the Montara spill that happened just before Deepwater Horizon off the west coast of Australia was a very waxy material. So during the night, it actually solidified where you wouldn't be able to disperse it. But during the day, it melted and it was dispersible. So that was a kind of an interesting example.
Okay, we got a question about the Mauritius spill. In that case, because it was near shore and near a reef, dispersants might not have been appropriate. Do you agree?
Okay. Well, based on, so we have, it was on that first slide that I had, so net environmental benefit analysis or spill impact mitigation assessment are some of the approaches we take to try to evaluate. But it's the balance of the trade-offs of doing one thing versus another. And there are some cases where you might say that whatever the sensitive species might be in the water or on the shore at the time could change your answer. So not knowing what the specific environmental ecosystem components were off the Mauritius coastline at that point, I don't know. But typically we would try not to disperse oil above a coral reef because of the long-term effects.
Well, we're running out of time and there's still a few questions. So my plan is to kind of capture these questions and I'll send them to Tom and I'm glad we have a lot of questions. I'll send them to Tom. That's one of the power of this online thing is questions can get asked. I'll send them to Tom and we can send out those answers to everybody after he has a chance to make up a really smart answer.
Oh yeah, okay. And again, if anybody ever wants to come and visit OMSET, just let me know when it's feasible again.
All right, so
thank you.
You've given back control, right? So Dagmar, if you want to get loaded up here, we'll go to you. All right, and so as she's loading up, I'll just tell you, so I decided to put Dagmar second because she's going to describe some recent work that she's been involved with to look at historic spills and test the rule of thumb that many in the oil spill response industry at least have on how much oil can be mechanically recovered. So she's done a study looking at the data that she has on historic spills and the estimates of mechanical recovery from those spills to test this rule of thumb that 10 to 30% of the oil during a spill can be mechanical recovered. Now that's from offshore. And I think Dagmar is going to say this, but I just wanted to say that I get accused at least of kind of over advocating dispersants. And I just want to say that dispersants have their place in offshore oil spills. Large offshore oil spills are in the right type of location. But mechanical recovery will always be the most important oil spill response option. We need to remember that because if it's possible to pick up oil and put it back in a container, we should pick up oil and put it back in a container. Dagmar is going to describe the challenges of that. But let's keep that in mind. We're not saying that mechanical recovery is important. It'll be used in 99.9% of the spills as we go into the future because they are amenable to that. We're talking about a small subset of oil spills that are challenged and where mechanical recovery is challenged. So let me introduce Dagmar and I'll give it over to her. So Dagmar Etkin, Dr. Etkin has been studying oil spills since 1982, including all aspects of oil spill response risk or oil spill risk modeling of probabilities of incidents, environmental impacts, and oil spill response. She has worked with both the oil industry and with federal and state oil spill agencies in the US and around the world. She received her PhD from Harvard in ecological modeling. So with that, Dagmar, I'll turn it over to you.
All right, thank you. Good morning, good evening, good afternoon, wherever you are around the world. Can you hear me all right? Is that?
Yes, I can hear you.
Thank
Great.
you. Thank you, Tim. All right, and you can see my screen.
Yep.
Very good. Now, this talk, this seminar series is not about mechanical recovery, but we did want to mention mechanical recovery because it is the primary response tool that we have in our toolbox, but we want to put a little perspective on that with respect to how it would compare to a dispersant response for large offshore spills. Oh, okay. Oh, there we go. So I've got a toolbox as well. You know, we always talk about the tools in the toolbox, of which mechanical recovery is one. And there are other ones that we've used. I included manual removal that's sorbents and that sort of thing, and all of the shoreline cleanup that we do, which usually is some kind of a variant on manual removal. And so this time I'm just going to talk a little bit about mechanical recovery as a tool in our toolbox. There are benefits to using mechanical recovery. Recovered oil can no longer impact the environment. There tends to be broad stakeholder acceptability. And this is because of concerns about, toxicity of dispersants and some of the, the air quality issues around in situ burning and so forth. But there are drawbacks. It tends to be labor and equipment intensive. There's an awful lot that goes into it. A lot of boom skimmers, people, involved, storage, disposal, all kinds of things that are involved. And that tends to be one of the things that makes it expensive too. As Tom, you were alluding to costs earlier. As a general rule of thumb, we've been told that about 10 to 30% of the oil is recovered by mechanical recovery. Now, I want to just look at that a little bit more closely. How reliable is that rule of thumb? Where did this rule originate? And how is it calculated? First, it's important to understand that the recovery calculation can be done several different ways. And here's an example. If you have 100,000 barrels of oil spilled and you've recovered, and assuming you can reasonably measure how much you've actually recovered mechanically, then the question is, well, what do you compare that to? Is that compared to what you had? First off, is that all oil? Is it oil and water? Is it emulsion? That's often an issue. We're not really sure how much actual oil we've recovered. And then if you compare the 10 to 30,000 barrels of oil, you compare that to your 100,000 barrels spilled, you might say there's a 10 to 30% recovery. But what if 40% of the oil has evaporated? That really only leaves, that leaves less oil that's available to actually recover mechanically. So in that case, you might say that 17 to 50% in this case of recoverable oil might be recovered. So we have to make sure we're using the same language here when we're talking about recovery rates. For the Macondo spill, these are sort of the calculations of recovered oil, mechanically recovered oil. First, it depends on how much oil you thought was spilled. There were different estimates of that, and there were different estimates of the amount of oil that was removed. So depending on how much oil you think was actually spilled and how much was available for removal, and anything that's available for removal here we're assuming is oil that has not evaporated or naturally dispersed and has not been directly removed at the wellhead. What we're not taking into account here is oil that may have been recovered or in some other way. So for mechanical recovery, we're not also now looking at, well, the oil that was burned wasn't available for recovery and the oil was dispersed wasn't available for recovery. We're just looking at any oil that's remaining after evaporation and natural dispersion, and discounting what was removed directly at the wellhead. And so you get varying, depending on if you look at available oil removed, you've got 5 to 8% of the total amount spilled. You get between 2.7 and 4% that we could estimate had been recovered. This is just one example. Usually our information about how much oil has been recovered and where this 10 to 30% rule of thumb may come from is coming from field observations and anecdotal data. The problem with this type of data is that it's, we've got questionable data on what the recovered quantities are. Are we talking about oil? Are we talking about oil with water in it? Are we talking about emulsion? My experience in this and collecting data since 1982 on oil spills is that people will report recovered oil, but it turns out what they're really reporting is recovered oil and water. So now we're not necessarily sure what our numerator is in our calculation for that proportion. There are also challenges in determining the total amount of oil spilled. We especially see this, of course, with well blowouts, and that gives us some question about what the denominator is. And then the question is also, what are we going to call our denominator? Is that the total amount spilled, or is it the recoverable oil, as we were talking about earlier? Typically, mechanical recovery will be reported as part of a mass balance. And this is just a completely hypothetical made-up example here. You've got mechanical recovery. Some of the oil has evaporated. Some of the oil is naturally dispersed. There may be some that is reported to be chemically dispersed. Some has burned, and some is reported to be ashore that would be then cleaned off in the shoreline cleanup process. And but it's based on the total amount of oil spilled. This is the most common way that we see mechanical recovery percentages calculated. But it's important to consider that there is another way to do it as well. And if you really want to see how effective mechanical recovery is in a field situation, you may want to consider what is actually recoverable oil. I looked at historical data on offshore spills and looked at 14 historical examples of large spills of over 1,000 barrels where offshore mechanical recovery was conducted, and looked at what sort of percentages we have. And there we found that there were reported mechanical recovery percentages which varied from about 0.1% up to 20%. And that was generally based on the amount of oil spilled, not on the recoverable oil. And then I found 24 historical examples of spills of that volume where offshore mechanical recovery was precluded due to the conditions at the time. And those would be 0% recovery. Again, offshore spills, very important point. We're talking about offshore spills. The average recovery rates based on the total amount spilled came to for these incidents, and I went through all of my databases to try to find every single example of an offshore spill where we had records of the amounts of oil that were mechanically recovered or what the response was. If you include the 0% cases for total amount spilled, and looking at total amount spilled, you get 2.4% recovery. If you exclude those 0% recovery cases and only include the ones where they actually were able to commence recovery operations and did some recovery, the percentage is 6.4%. Now, if you base that, I was not able to do very extensive mass balances on each one of these spills, but based on the type of oil that it was and what we know generally about the amount of recoverable oil after taking into account evaporation and natural dispersion and that sort of thing. If you base it on just on the recoverable oil, you now get a 5.6% recovery rate when you're including the 0% cases. And if you exclude those 0% cases where they wouldn't be able to recover anyway, now we have a 15.3% recovery rate. The factors that limit offshore oil mechanical recovery rates are based on the properties of the oil and the behavior of the oil, the environmental conditions, and operation and logistical issues. In terms of the oil properties and behaviors, Tom talked a little bit about this, but the oil spreads and thins out often to less than 0.1 millimeter very quickly, and that reduces the actual encounter rate with oil that any booming and skimming system might have. There's patchiness, the drifting of the slicks reduces the encounter rate. And one thing I should, should point out here is that we're also talking about an issue of scale. When you saw the pictures that Tom was showing you, when you in these large offshore spills, your encounter rate is going to be reduced, and trying to chase that oil around gets very difficult very quickly. Viscosity and waxiness can reduce the efficiency of skimmers. There are different types of skimmers that are able to handle more viscous oils and so forth, but in general, it becomes an issue for most skimming systems. Emulsification increases the viscosity and also increases the recovered oil and water volume. Now you have a lot more oil and water that you need to deal with in terms of storage, and especially if you can't decant, it becomes an issue quickly. Environmental conditions. You often have high currents, which can cause entrainment and lower boom effectiveness. So if you're not containing the oil, you're not able to mechanically recover it. If you're, just checking my timing there, if you're encountering high winds and high sea states, that can affect boom effectiveness as well as operational safety for responders. High winds will start spreading the oil, again, reducing the encounter rate. In some circumstances, you need to deal with ice and debris, and that can clog skimmers or damage the boom. Visibility is an issue. Fog, glare, darkness can all impede operations. You need to be able to see the oil, although we now do have some means now to detect using remote sensing to detect oil, but in general, a lot of it is done through overflights and looking to see where the oil is so you can properly position your equipment. There are some significant operational and logistical issues that can reduce the effectiveness of mechanical recovery. An offshore location relative to where your equipment stockpiles are and the logistical support are can affect operations and often cause delays. You have to get out there. You have to get your equipment from the shoreline, or get it first to the shoreline, and then from the shoreline out to the offshore location, and that can cause delays. And as we have delays, the oil is spreading. Oil water storage and separation capacity and decanting rules may create a bottleneck. Decanting would be if you are allowed to pour, after separating the oil and water, if you can pour the water back into the environment. There are a lot of regulations about that, and if you are not able to decant because of the regulations, that means you now need to store the oil and water. You need to bring it back to the shoreline or someplace else where you're going to separate it and then process it. The operator's skill and experience, the efficiency of aerial support and remote sensing, and just response management overall will affect the operational effectiveness. And in a large offshore spill, these become very complicated issues. Again, we're talking about offshore spills here. Mechanical recovery, the mechanical recovery limitations that I've mentioned apply to large offshore spills. More common, smaller nearshore spills will still best be handled with mechanical and recovery and manual recovery methods. You have your logistical support close by, and the severe environmental conditions of the high winds and the high sea state and so forth are of less concern. So that will always be an important tool in the toolbox. So the takeaway messages from me today are that oil behavior, environmental conditions, and operational and logistical issues can hamper the effectiveness of mechanical recovery offshore. Mechanical recovery for large offshore spills averages about 2 to 6% based on the total amount spilled, or if you want to consider the recoverable oil, you might say it's 6 to 15% that we've seen in actual historical cases of larger offshore spills. This still leaves a significant amount of oil in the environment, depending on weathering and other cleanup that's going on. And then also mechanical recovery may still be the best approach for smaller nearshore spills. And that's all I have.
Great,
So,
thanks, Dagmar. You came
right.
under the wire there, so we're getting back a little bit of time.
Okay.
We have a few questions, and
All right.
I'll start reading them off to you. So the first question is regarding the historical spills analyzed for mechanical recovery rates. How long ago were these? Is it mainly, yeah, see what type of mechanical recovery was used back then, given that modern means have much higher efficiency. So the question's about how long ago were these historical spills, and then were a lot of them based on less efficient mechanical recovery from 30 years ago compared to what they might be today?
Oh, that's a very good point, and the challenge was actually to find. Should I stop sharing my screen here? Or, I don't know, how's this work?
Yeah, you can, and I can.
I guess whatever. Okay, so that's a very good question. I mean, we certainly have newer mechanical recovery methods. We're getting better at it in many ways. So certainly you might see higher rates of, you'd think you'd see higher rates of recovery in more recent spills, but that's not really what I saw. I mean, I did look at spills going back at least 20 years, but I could look at it again to see if there's a distinct pattern of higher recovery rates more recently. But to be honest, I think that we probably don't have enough data to actually make that sort of analysis in any statistically valid way. There just really aren't that many examples of large offshore spills where we have reasonably reliable reports about how much was recovered. But that's an interesting question. I will pursue that further. I'll look back into the data to see.
Well, Dagmar, we do have the Macondo incident, right? And you did a lot of analysis.
That's our most recent, and certainly we brought every piece of mechanical, good point, Tim, every piece of mechanical recovery equipment anywhere that was available out there, and had the best minds and most skilled people working on them, and certainly we didn't see very high rates there, as I reported earlier. So I'm not sure that we would suddenly see 90% recovery. Now again, a lot of the very efficient recovery numbers that you may see are for inland spills or for spills that occur like in a port or in calm waters or something like that, and those sorts of places, like especially some of the work that's been done with Elastec and so some of the newer mechanical recovery equipment and methods, we can see very high rates of recovery, but that's not the kind of spill that we're talking about here, these large offshore spills.
Yeah, I would just add that, I always say that, the laws of physics kind of govern what's going on with an oil spill. And we have a lot more efficient equipment. There are better skimmers, booms. The physics of keeping oil in booms is a big challenge. Mm-hmm. We don't have boats that from 20 years ago, boats go about as fast as they go today as they did back then, right? And the oil behavior hasn't changed, right? So when an oil slick gets to be 1/10 of a millimeter thick, the swath width that you can capture, you just can't capture very much oil in a boom.
Right.
And if Mother Nature decides to be in charge of the oil spill, you're not going to keep oil in a boom, right? It's the laws of physics. And I always say that until a green man comes down from Mars and tells us how to break the laws of physics, we're stuck with the laws of physics from both keeping oil in booms, which is often the limiting factor, oil spreading so thin that you just can't capture too much. And then another big factor is we can't go very fast, right? Boats without pulling a boom don't go that fast, right? Considering how fast an airplane or a helicopter can go. But if you're pulling a boom, you really can't go very fast, right? So it's this capture, it's this encounter rate that Tom talked about.
Right.
Those things fundamentally haven't changed, and I don't know how they change, right? We can make kind of incremental advances on some of this equipment, but we really need a step change advance to go from the 6 to 15% numbers to something over 50% to make mechanical recovery really a key response option to
Right.
environmental
Well,
impact.
one of the things that I've discussed a lot with Al Allen and Tom, mentioned our colleague, our highly esteemed colleague Al Allen, who has so much experience with this. One of the things that we've talked a lot about, in terms of creating models to simulate spill response and effectiveness and so forth, is you have to chase that oil around, and you need to be most effective, to have a highest encounter rate. You need to know where the thickest oil is. The oil has to be a certain thickness to be able to be reasonably recovered with the skimming systems. And one of the ways that we have some advances that we have had is through remote sensing. And I know the Coast Guard, I did some work with the Coast Guard a number of years ago, looking, well, if we were able to detect where that thick oil is, how would that affect things? But it would, so you might say that kind of that sort of data overflights, where that's where the thickest oil is, now send everybody over there, and that might work early on in the spills, but pretty soon things spread out pretty quickly, and that's not that's not really going to help all that much, but it's something to consider.
We might be able to get through. Well, we're getting more questions. Let me just answer a couple questions here that I can answer. Do you have this information published? And Dagmar and I have a paper it's in Marine Pollution Bulletin. It's been accepted. We have to make some kind of minor edits to get it published. So we expect it to be out in the next few months, at least, if hopefully before the end of the year. So this information will be in a peer-reviewed publication shortly. Another quick question, Dagmar, are there requirements that would allow you to decant during mechanical recovery?
That depends on where you are. And that's going to be up to the Coast Guard and the captain of the port and the federal on-sea coordinator, whoever's in charge out there. And in some cases you can decant, or you are able to, allowed to decant. In other cases you're not. The way that would help is that it now means you have less oil and water mixture that you now need to transport to the shoreline, and it could reduce that bottleneck, because if when you're offshore and you've filled your storage bladders or tanks or whatever you're using to store the recovered oil and water, when that fills, now you need to go get rid of that and come back or switch to a new thing. So that can become a bottleneck. So decanting may help to some extent, but that's going to be dependent on the laws, and to some extent the decisions made by the federal on-scene coordinator here in the U.S. at least. Okay,
thanks, Dagmar. We need to move on, and there's a couple more questions, so I'll send the questions to you, and we can figure out a way to respond to those questions as well. But thank you very much. That was excellent.
Thank you.
All right, share.
So I have to stop sharing. Oh, I did stop sharing.
Okay. Stop. All right. And I'm going to bring up my slides, hopefully. All right, you can see my slides?
Yep.
Okay, well, let me introduce myself again real quickly. Tim Nedwed, I work for ExxonMobil, and I've worked for ExxonMobil since 1998, and I've led the oil spill response research program. Actually, it's oil spill response, the oil spill response research program. And I've led that for over 15 years now, and so my job, I tell people I have a great job because I get to come in every day and kind of scratch my head and figure out how we can do a better job of responding to oil spills. And one focus has been kind of how we respond to a catastrophic large offshore oil spill. So that's one of the things I do. But another thing I do is oversee dispersant effectiveness testing and fate and effects studies. And this talk I'm going to give is kind of some of the learnings I've come to, realizations I've come to over the last 15 years, looking at fate and effects studies and dispersant effectiveness studies. So the title of this talk is Challenges of Translating Findings from Lab-Based Oil Fate and Effects Studies to Conclusions Relevant to the Real World. So I'm going to talk about the challenges of doing toxicity studies, the challenges of doing biodegradation studies, and the challenge of doing dispersant effectiveness studies in a closed system. And I'll say here at the beginning on this title slide that it is impossible to represent the real world, an open system with an infinite open system, the middle of the ocean or even the Gulf of Mexico or a large body of water. It's impossible to represent that in a closed system. certainly impossible in a beaker for a number of reasons that I'll describe, or even the largest closed system that we have, which is the OMSAT wave tank, is still a closed system and doesn't allow all the things that would naturally occur in an open environment. So the reason I'm giving this presentation is because there's a lot of literature that's come out over the last 10 years, and I think a lot of these issues are not described in the literature at all, or if they're described, they're not, the conclusions don't take some of these issues into account. And so the goal here is to kind of communicate these issues so everyone can become more aware of them. Okay, so here's what I'm going to talk about. I scratched off the first item there because I'm leaving that slide in there because I'm going to publish these slides and anybody can look at them. But I did a practice of this talk last night and I went way over, so I'm cutting out that slide, but you can look at it. But I'm going to talk about the fate and effect studies and the dispersant effectiveness testing. So first I'll talk about toxicity testing, then I'll talk about biodegradation studies, and then the dispersant effectiveness test. And I'm going to say, as I said, you can't represent the real world in a beaker, but the challenges that we see and the issues that we see, I believe, negatively impacts, right? Makes things appear more toxic than they might be in the real world. Challenges biodegradation, the rates of biodegradation, the extent of biodegradation, and has negative bias in the effectiveness of dispersants. I'm going to give kind of high-level discussion of these issues. We're going to have a specific talk by Tom Parkerton on toxicity testing, and he'll go into more detail on those issues. And we're going to have another talk by Roger Prince in a couple of weeks on biodegradation research that he's been doing for the past 30 years or so, and some of the challenges he's seen and protocols that he's developed. So I'm going to describe all of these issues, but I'm just not going to complain about them. For each one of these, I have a slide that kind of at a high level shows what we think are some of the resolutions for those issues. And I have down here in a box here, dispersants are sometimes the least bad response option. And it's important to keep that in mind because a lot of the research that goes on focuses on being critical of dispersants without looking at the big picture. The reason I had Dagmar give the second talk here is because any response option, dispersants, in-situ burning, natural attenuate, anything that you choose has a lot of challenges, right? If you myopically look at mechanical recovery and you looked at the data that Dagmar came up with, you'd say 6% recovery. It's not much better than letting Mother Nature take care of the oil spill. So you could be very critical of mechanical recovery. Mechanical recovery has the obvious benefit of getting oil out of the environment and putting it back in a container. But if you leave 90+% of it in the environment, because you're focused on that option, it might not be the best option to protect the environment. So dispersants are sometimes the least bad option, but you need to consider them with all the other response options and the limitations and advantages of all response options to come to a good conclusion. So this slide has a lot of words. I put a lot of words on purpose because, again, it's going to be published. But this kind of summarizes some of the things. So estimates of real-world impacts from oil spills are often based on toxicity, biodegradability, and dispersant effectiveness tests. And they're performed in glassware in a lab and sometimes in larger wave tanks all the way up to OMSAT, as I mentioned. But to me, it is fairly intuitive that oil dissolved, dilutes, and spreads very differently in a beaker than it will in the open ocean, right? But what is less intuitive, in my opinion, is how these differences bias fate and effect studies, right? So just understanding that they do bias fate and effect studies and which direction do they bias fate and effect studies. But then it's also important to understand how they bias fate and effect studies so we can compensate for them as we try to extrapolate findings from lab-based tests to what we expect might happen in the real world. So as I said, these differences can lead to oil appearing more toxic than it is, unrepresentative dispersed oil biodegradation tests, and negative bias inherent in closed system dispersant effectiveness testing. So I'm going to start with toxicity testing. So toxicity testing, the goal of toxicologists is to measure an impact to organisms, right? So often they have to use extreme exposures in a beaker that is not representative in the real world. So I put a couple of issues here. This isn't the first bullet there, reporting nominal versus measured concentrations. What I mean there is when you do a toxicity test where you use dispersants and compare it against the toxicity of the oil by itself, when you just report the amount of oil you put in the system, that's the nominal value. then you are going to bias things against dispersants, because the goal of dispersants is to put oil into the water column, and sequestering the oil and dispersed and dissolved oil in a beaker makes the organism encounter much higher concentration than they would for a given nominal concentration compared to not using dispersants, where most of the oil stays in the slick on top of a beaker. So that makes dispersant treated oil look far more toxic, and there was a number of examples of that being published in the literature. It doesn't happen as much as it used to, but it can still be an issue. And then just the exposure conditions that an organism encounters in a beaker is far different than they would in the real world. Most toxicity tests are 48 to 96 hours, and they use relatively constant concentrations, whereas dispersed and dissolved oil in the open sea dilutes extremely quickly, right? This chart here shows some actual real world data collected by Bargerano in a paper published in 2014. So a bunch of researchers went out and collected samples of oil, dispersed oil, underneath slicks, and you can see on this graph here what the depths were, so quite shallow, 1 meter below the slick. And the x-axis is time and the y-axis is concentration. So you can see even the maximum concentrations that they measured were less than 60 parts per million. But in less than an hour, the concentrations are going back down to extremely low. And in a couple of hours, we're down, as Tom mentioned in his talk, to concentrations on the order of a part per million. And considering that biodegradation, colonization of oil droplets, biodegradation, takes an extreme amount, it takes 24 or more hours, right? The concentration that organisms are exposed to over time is highly variable, and for most of the time, especially during a 48 to 96 hour toxicity test, most of that time the concentrations are actually quite low. So again, these organisms are exposed to extreme conditions, and you need to account for that when you try to extrapolate results to the real world. But a couple of other things that are maybe less well understood perhaps, but there's unrepresentative exposure in beakers because we allow an equilibrium to happen between the dispersed and the dissolved oil. That's between droplet oil when you do a test where you use dispersants to put droplet oil in the water column, or when you use a test where you use high energy. And then you have equilibrium between the oil slick and the dissolved oil when you use a lower energy test. So these pictures on the left here show two methods of making stock solution that are commonly used for toxicity tests. This big jar on the right is what a high energy water accommodated fraction might look like, where you put a lot of energy in the system. So even if you didn't use dispersants, you get a lot of droplet oil. You can force droplet oil to go into the water column. Or CWAF is chemically enhanced water accommodated fraction, which means that you use dispersants to disperse the oil. In both cases, HEWAF or CWAF, the oil looks pretty much the same because you're forming small droplets. Water accommodated fraction, when you don't use dispersants and you allow natural dispersion to happen, this is what a stock solution might look like when you do that. The point of this slide is that in these systems, the dissolved oil comes to equilibrium with either the water droplets that are in the water column for these HEWAF or CWAF systems, or the surface slick in the WAF system. But because there's much more surface area of the oil in the HEWAF and CWAF, you can get much higher concentrations. And you can look at the literature, but dissolved oil components are the primary driver for acute toxicity. And so the concern here is that allowing even one equilibrium to happen in the stock solution is not representative of what happens in the ocean, because there is no boundary, and diffusion and advection in the open sea does not allow these high concentrations to happen, and actually doesn't allow the same composition of droplets to happen. And that composition and concentration is changing over time. Composition of the dissolved components. And the result is you can get concentrations in a beaker that are significantly greater than they might be in the field. The second issue is very similar, but it's because of the kind of common methods of making dilution for toxicity testing. So in a toxicity test, you make a dilution series over a range of concentrations where you think you might see the effect that you're at, or either the lethal concentration. And a common method is to determine the lethal concentration that kills 50% of the organisms in a beaker, or an effects concentration that affects 50% of the organism, changes their behavior in some way. But there are two common ways of making this dilution series, right? One is called variable loading, and the other is called variable dilution. both of them allow equilibrium to happen, right? So you start with a stock solution. Under the variable dilution method, you use one high concentration stock solution. So now you have, it's either a WAF or a CWAF or a HEWAF. You have a high concentration, you get a high concentration of dissolved and dispersed oil in the water for the HEWAF and CWAF, and then you make dilutions. And when you do that, you have the first equilibrium of the stock solution mixing, and then you take it out the amount, and then you dilute it with the seawater that you want to use in your test, which allows a second equilibrium to happen, right? And then you can do that multiple times to get the different concentrations that you're after in your testing. The challenge with that is that, number one, you have two equilibriums, which is unnatural, but the droplet oil acts as a buffer for the dissolved phase. So you have a certain concentration in the stock solution of dissolved oil, but by diluting it and allowing the dispersed oil to come to a second equilibrium, you're releasing the toxic components to the dissolved phase. So it can make the oil, dispersed oil or HEWAF, look much more toxic than it is because you have a buffer for the dissolved phase in this system. It's less of an issue for WAF because you don't have so much dispersed or droplet oil in the system, so you can get a dilution where the dissolved phase dilutes, especially at higher dilution ratios. The other method of doing it is this variable loading method, where you make different stock solution based on the concentrations of oil that you want in your dilution series. We would recommend that as probably more representative, but again, this single equilibrium is still not representative of what happens in the real world. And because of that, I'm still going to reiterate that it is unrepresentative of what would happen in the real world. And note, for all these kind of issues, I have some references that you can go look at to see to get more information. All right, this is even less understood, I think, but some researchers at the University of Minnesota and some research that we've done with the API shows this issue of leaching of surfactants from oil droplets. And so when you think about it, that leaching is unrepresentative because if you're for toxicity testing, because you're exposing organisms. So if you're doing a toxicity test on dispersant treated oil, you're sequestering organisms in a beaker with both the dispersants, the surfactants in the dispersant, and the dissolved phase of the oil and the droplet phase of the oil. But I say it's unrepresentative because in the real world, at least the most water-soluble components that are put in the oil when dispersants are added leach out of the oil droplet very quickly. And I'll show you what I mean. This image on the left here is a downflow column that we built at Sintef in Norway. It allows seawater to be flow with a pump. It flows downward into this column, and we can put dispersant treated oil droplets and inject them into the base of this. By controlling the downflow rate, we can control the size droplets that we get into this neck here of the system. And then in the neck of the system, we have a camera, so we can video a droplet as if it's rising at its terminal velocity in a large deep water column. So we can video it for long periods of time and look at its behavior. So this video here is a droplet, and this is about a 1 millimeter droplet. And let me stop it. It's about a 1 millimeter droplet. It was pre-treated with dispersants at a ratio of about 1 to 100. It's a very light oil. I believe it's Oseberg oil, which is the surrogate we use for Macondo oil at Sintef, because it has properties very similar to that. The important thing to see here, and this video is going in real time. So we are looking at the droplet, and water is downflowing, and so the droplet is basically at its terminal velocity. The important thing to notice at the beginning is this kind of oblong football shape. But very quickly, right, you can see, even almost in real time here, that the droplet is starting to round, right? And so now we are at just over, what, 15 seconds. And within 30 seconds, this droplet, and the video is going to stop here, but within 30 seconds, the droplet becomes very round, right? And what that means, the only way that could happen is if surfactants are leaching off the droplet. So I think it's the dioctyl sulfosuccinate, the DOS, because that's the most water-soluble component in the oil. It is leaching very quickly within 30 seconds. And so what that means is for a droplet, especially a droplet this large that has a high vertical force because of gravity, so it's rising very quickly, that droplet has a different fate than the surfactants that leach off of the oil. Right, so it means that trying to represent a system like this in a beaker that doesn't allow the surfactants and the droplets to have different behavior. It means you're sequestering the oil droplets with surfactants, and that's not what happens in the real world. The leach surfactants travel with the currents, right? They don't have a gravity component, but the droplets continue to have a strong gravity component, and the larger the droplets, the more that component is. But all of the droplets have a certain amount, have a certain gravity component. They're always positively buoyant. So sequestering droplets, oil, and surfactants in a closed system for long periods of time is not representative. So this is really important for understanding subsea dispersant injection in deep water, because there might be a lot of time where the droplets are rising through the water column. But it's likely important for surface application of dispersants, because you are still trying to put droplets in the water column, and there is still a vertical component to the rise velocity of those droplets, whereas anything that leaches off the oil and is dissolved in the water column is moving with the currents. And I've put here, I think it's also important for MOSFET application, where you're trying to assess the impacts of dispersants on the formation of marine oil snow. So as I said, I have some recommended practices for toxicity effects, and I'll go through this quickly because I'm running out of time, but you can read this later or ask questions. So toxicity testing is important to do. And the reason it's important is because it needs to be done to validate toxicity models, right? So if you're developing toxicity model and you can't have the model predict the effects that you see in a closed system where you can very carefully control and understand the conditions, then your toxicity model may need to be fine-tuned to make it more valid. But ultimately, you use an oil spill fate model to predict the dissolved concentrations of components from the hydrocarbons in the field if your goal is to predict acute toxicity. And then you use the validated toxicity model, and there's a toxic unit model that is described in the NASEM report that Tom mentioned, that should be used to predict effects levels that you would see in the real world. So toxicity tests are used to validate toxicity models, but then you use models to predict both the dissolved phase concentration and the toxicity, so you can predict effects levels in the field. That's our recommendation. And Tom Parkerton in a couple of weeks will talk about that in more detail. So quickly, biodegradation protocols. The issues with both biodegradation protocols, a couple of them I've listed here, is first, the papers that we see compare naturally dispersed oil to chemically dispersed or surfactant dispersed oil, so chemically dispersant treated oil. But the comparison should be between a surface slick and the oil that's dispersed in the water, dispersed and dissolved in the water column. And that's because the decision not to use dispersants can leave a significant amount of oil on the surface as a surface slick that can remain there for long periods of time and eventually land on shorelines. But the effective use of dispersants moves oil to the water column as small droplets, right? So the comparison should be between biodegradation of a surface slick and dispersed and dissolved oil in the water column. And then the second issue here is the concentrations of oil are often orders of magnitude too high. So if you go back and look at the literature for the past 30 years, you get concentrations often on the order of 100 parts per million, and I've seen literature up to 4,000 parts per million of dispersed oil in the water column in these closed system tests. And I showed this chart before, but that's just not reality. Microorganisms are exposed to concentrations much lower than that, especially when you consider that it might take 24 or more hours for a droplet to be colonized and for biodegradation to become significant. At those times, those multi-day kind of lag periods, the concentration of dispersed oil that the organism will be exposed to is on the order of just a part per million or maybe even less. So another less known issue is when you're making up mesocosms, right, we recommend that you use low concentrations on the order of 3 parts per million or less. But what happens when you use 3 parts per million in a closed system like this and you use a stir bar at the bottom? This series of photographs here show when you go to the right, you show systems that are generated with different concentrations, 2.5 parts per million up to 300 parts per million. And then we observe these systems mixing. There's a Teflon stir bar on the bottom of these beakers, and it's mixing over time. So we took photographs of them over periods of days. When you use low concentrations, which is what we recommend, you have a challenge. Both the dispersant treated oil and the untreated oil spreads very thin and naturally or chemically disperses. So over time, you have dispersed oil in the system that looks the same regardless of whether or not you use dispersant. So when you come out after a 40-day biodegradation test, there's no wonder that you don't see much difference between the naturally dispersed oil and the surfactant treated or the dispersant treated oil. The issue, when you get above 50 parts per million, or maybe above 20 parts per million, but our next step here is 50 parts per million, but it's easier to see at the 300 parts per million concentration in these photographs. when you use higher concentrations, then you have a system with and without dispersants. On time 0 and for day 1, when you use dispersants, you get this nice dispersed oil system. When you use dispersants and when you don't use dispersants, you get a slick that remains on the surface. But when you come back 24 hours later, and you can see it in this image, coalescence causes the oil in the dispersant treated system to come into the vortex, and you get a surface slick. And it's not as clear in these photos, but you can certainly see the difference between time 0 on all of these and time 3 days. But after 24 hours, you pretty much have the same system. Clear water that looks as clear as drinking water, regardless of your initial concentration, regardless of whether or not you use dispersants, in both systems. So you fundamentally have the same amount of surface area in both systems over the life of your biodegradation test. So again, it's no wonder that things are confused, because you see the biodegradation rates that might be comparable with both systems. So our solution to that, and this is a solution that Prince and Butler came up with, and you can see more details about it in their literature, but they have this simple floating boom system where they took a glass pipette, cut a little section out of it, and they put a O-ring around it to act as a kind of flotation collar. And they put small concentrations. Our recommendation is less than 2 to 3 milligrams in their system. So they put the amount of oil either inside this pipette glass with dispersants or without dispersants. And then you put them into your mixing system. The dispersant treated oil will go into the water and stay as a dispersed oil phase for the duration of your experiment. But you won't, even though you're using low concentrations, this system forces the oil to remain as a surface slick in the untreated system. And you can go look at their paper, but you see significant differences in the rates of biodegradation and the total amounts of biodegradation when you use a system like that, which we believe is more representative of what will happen in the real world than other methods. So the last thing I want to talk about is the dispersant effectiveness testing. And as I said, negative bias. Tom Coolbaugh and I have a paper that's in the 2008 IOSC proceedings. But here's the issues with dispersant effectiveness tests. Beaker-based tests last only 10 minutes or so, and even a wave-based test at OMSAT lasts 30 minutes. Mother Nature doesn't stop putting mixing energy after a few minutes when you use dispersants in the real world. So longer periods of time, so much more dispersion can happen in the real world. Another issue is the walls of beakers and basins physically limit the spreading of oil slicks, and I'll show you why that's important, because I believe that sheening of oil slicks in the real world is an important mechanism for dispersion, and dispersion of very small droplets that are effectively dispersed. And then something that's less well understood is that herding caused by the surfactants from dispersants limits the spreading of oil slicks. And this little cartoon on the left illustrates that. These A series of images here show you kind of the standard way that I used to use to show how dispersants are applied. You drop dispersants from some sort of aerial system. They kind of nicely only land on the oil slick. They go to the interfaces, and then they cause dispersion to happen when mixing energy happens. That's kind of the conceptual images we've used to explain dispersants in the past. The reality is surfactants, the dispersants overspray off the slick, and then they go to the interface of the water, lower its surface tension, and cause herding effect. And they keep oil slicks from artificially spreading. This happens in a beaker, it happens at the OMSAT tank, and it happens in the real world. In the real world, these, over longer periods of time, these monolayers of surfactants that might be on the water surface are very fragile, and they get dispersed into the water themselves. This allows sheening to happen. And almost all oils, this table shows information on the interfacial and surface tension of the oils that I found available on Environment Canada website. And you can determine whether or not an oil should sheen based on the knowledge of the interfacial and surface tension and knowledge of the surface tension of water. And I calculated almost all oils in clean seawater should sheen. There's only one oil, this very heavy fuel oil, would not naturally sheen. But if you go to the OMSAT tank, and I've seen hundreds of tests probably at OMSAT, oils don't sheen on the OMSAT tank because it doesn't take much contamination from surfactants for the oil, for that to reverse. And the low interfacial tension caused by surfactants on the water keeps the oils from sheening. So just a quick video of what that does. These test pans are pans of seawater. This one on the left has been treated with 3 drops of 9500 to simulate overspray. This pan on the right wasn't. Right? And the oil, we have a little tube with 10 mils of oil placed in it in both of them. So the one on the left is oil that wasn't treated with dispersants. Neither of these oils were treated with dispersants, Alaska North Slope crude oil. But the one on the left is spreading in a pan that's contaminated with invisible surfactants. The one on the right is in a pan of clean seawater, which has high surface tension. So the point of this is you can see the different behavior. This is what we're doing in dispersant effectiveness tests in a wave tank, like the onset tank, and in beakers, you're keeping oil artificially thick. In the open ocean, the surfactants on the perimeter on the water surface will go into the water column with limited mixing energy, and then you have these thin sheens around the end. This one is actually artificially thick because of the walls of the system. But you can just envision that this thin sheen on this slick is much easier and will disperse much more effectively with low energy than this thick blob of oil on the right. So our recommended practice for dispersant effectiveness testing is dispersant effectiveness tests are used for relative characterization of dispersants. So is this dispersant better than that dispersant for this crude oil? Or it's used to determine which crude oil for a given dispersant is more dispersible than the other, but it can't be used to tell you what you can expect for dispersion effectiveness for an oil spill in the real world. And we mentioned this earlier, but you need to conduct field tests during an actual spill to determine if that oil, the oil that has spilled and has undergone the weathering that it went in the field, is actually dispersible. And there's a number of tests that can be done to do that in the field. So I'm running out of time here, and I won't go through this, but I'll leave this up. I don't know if we have time. I have time to stay on and answer questions for anyone who's willing to stick with us, but we run out of our time commitment right now. It is 1/2 the hour, but I'm happy to stay on, and I don't know about Dagmar and Tom if they have questions, but if anyone that's willing to stay on, we might be able to go through some more of these questions, and I can answer a couple of questions. But I really appreciate everyone taking the time to stay with us. We had a very good turnout. I think we maxed out at 190 participants, and in my mind, that's excellent for this kind of talk and presentation. So I appreciate everyone's time. So why don't I see if for those that want to stay on, I'll see if I can find a couple of questions relevant to my talk. Let's see. Okay. Also difficult to compare lab test standard species to other species. Yes, and life stages. Additionally, life stage has a huge bearing. Young are generally more susceptible than adults. Yes, that's true. Lots of information needs to be weighed. Yes, so we've got a comment here, I guess, that it's very complicated. Yeah, so we have a question. Typically, do you see any difference on the impact on biodegradation when comparing chemical dispersion versus mechanical dispersion, or are they basically the same? Yes, so if you, as I showed in the slide, if your comparison is biodegradation of a surface slick versus oil that is effectively dispersed in the water column, we see significant differences in the amount of biodegradation and the rates of biodegradation, simply because you have more surface area for biodegradation. And at a high level, it's the key to making biodegradation happen quickly and aerobically is to get a lot of surface area and to allow enough dilution so that you're not exhausting the available oxygen or nutrients that are available in the marine environment that the dispersion is happening. So, but if you're looking at naturally dispersed oil that is effectively naturally dispersed, which means that it's a certain droplet size distribution, the droplets that stay in the water column over time, versus dispersant treated oil that's in the water column, the dispersion, the amount of dispersion, the rate of dispersion is about the same. And I would say it's even might be biased because in a beaker, as I said, you're keeping the surfactants sequestered. If the surfactants have any impact on it, which I don't think they have any significant impact on it. But the naturally dispersed oil that stays in the water column versus chemically dispersed oil, the biodegradation is effectively the same. And I think we'll have a talk where we can go into more details on that in a couple of weeks. All right, here's another question. In the downflow column video, it appears as though the total volume of the oil droplet changes through time as the size shape changes. Is this because of the angle of the camera? Yeah, so in these experiments, we noticed through our experiments, and so this is, the oil that goes into that system is dead oil, right? We didn't use live oil, right? Dead oil is is oil that has undergone separation of the volatiles before it's put into a pipeline or into a tanker. So most oil spills are dead oil. The volatiles have been removed for safety reasons. So the oil that went in that system was dead oil. We did measure the difference in over longer periods of time than that experiment, hours. And we noticed that those droplets might lose 5% or so of their volume over time. So it wasn't significant. It wasn't a significant factor in that would change the rise velocity of those droplets. So I think it is the shape change, and then the droplet can move closer or further away from the camera that might make it look like it's changing significantly. I mean, if 5% is important, right? But it is not enough to really change the rise velocity of those droplets by a significant amount. Let's see if we have anything. I typed in that we're going to try to make the presentations, at least the hard copies, available. We are recording the presentations, but I'm going through the hoops that I have to go internally to make sure that that we are going to be allowed to publish the recordings themselves, which I hope to, and I'm making my way through those hoops. So it depends on whether I can get all the way through the hoops and whether or not the presenters will allow their recordings to be distributed. Okay, another question. The protocol of Prince and Butler is hard to scale up. What say you to those wanting to work in the 100-liter plus scale? Well, I'd argue that scaling up just means you need a bigger booming system to keep the oil from naturally dispersing. But I'm not an expert on that, and that question is a good question to ask Roger Prince as when he talks in a few weeks. But I can envision how you would scale that up. Everything just needs to be bigger, and the booming system needs to be such that it's not so big that it is influenced by the mechanical mixing system that you use in the tank to get an artificial amount of.
Hey, Tim,
dispersion.
didn't Cedra do something that was on a larger scale where they basically had these floating systems that sat in the harbor right there near them?
Yeah, the nearshore dispersant testing that they did. Yeah, so
yeah, they were autonomous, these floating things that did keep it open at the bottom. Yeah.
Yeah, so I mean, in my mind, the key is to not let the oil spread too thin. That natural dispersion can happen and be quite effective, right? So if you use a booming system that keeps the oil thick enough, that I'm not sure why scaling up would be too big an issue. The key thing that we're trying to do is keep natural dispersion from being as significant as dispersant treated oil slicks. Okay, when we're using boom to contain the oil to utilize mechanical recovery, aren't we creating a possibility for an equilibrium to appear, and/or doesn't that make it more toxic as a result? No, so the equilibrium doesn't happen in an open system, right? Because Mother Nature doesn't like things to stay concentrated, right? So any oil components that dissolve in an open system are going to advect and move away. Based on the currents, but just natural advection away from it because of a concentration gradient. So you can't build up an equilibrium in a boom system within any distance of the oil slick. So no, I don't think you can have equilibrium happen in an open system like you would in a closed system in a beaker. Let's see here. So a couple of these questions, we'll go after those afterwards. Let's see if there's something I can go back on that I missed that was asked to Dagmar and Tom. I have to say this question and answer system here is not the most easy to read through. We talked about, yeah. So so this is for Dagmar, are we maintaining a library of real incidents to learn how they were handled and what were the learnings? Dagmar, you want to?
Sure. Are we, first of all, the question is who's we, maintaining a library? I certainly, as many of you may know, have been keeping databases of oil spill incidents since 1982. So I have little case studies, where I keep track of these things. I don't know where else it is being tracked. It certainly is something that we should have. We should have, lessons learned from past case studies, and in order to detect longer term trends, it would be helpful to sort of keep adding to that as we move forward with other incidents in the future. So but I don't know, who else is collecting this.
Yeah, I'd say Dagmar is the only person I know that is consistently collected. She has a large library of oil spills,
Easy
and
enough.
quite a bit, because she has the largest library of case studies of oil spills that have happened over the past, 30 plus.
Yeah, I mean, since about 1968 or so, it's like where we go back to.
Yeah.
Yep.
We have, so there's a lot of questions about this Mauritius example, and we talked about that a little bit, and I'll just give you my thoughts on it. So Mauritius is one of these places that's quite remote and quite challenging, right? And it doesn't have a huge kind of internal oil spill response capability with mechanical recovery. And that might have been an example if it had kind of a Gulf of Mexico capability for mechanical recovery, where that oil could have been boomed around the ship and maybe something happened to it. But I do understand that a couple of storms came through and actually caused the tanker to split in two. And there again, Mother Nature will take over when that happens and put the oil wherever Mother Nature wants to put the oil. I don't know the details of that. There's a lot
Well,
of
there's an update to that. They actually collected some of the fuel from it. Apparently it's on a barge and a tug was moving it and the tug sank.
Yeah.
And apparently it killed 2 people.
So it is that when you get to the nearshore environment, it's quite challenging. So I'd say you shouldn't rule out the use of dispersants in that situation, right? Number one, because the availability of mechanical recovery is quite challenged in that environment. The conditions near an environment like that can be quite energetic, especially if a storm comes in. And without, if you are focused on mechanical recovery and you can't do much, then you're going to let Mother Nature take over. There's comments here that the oil might have gone into a lagoon and stayed there. I would suggest that if you're outside near the reef, outside of a lagoon, and you disperse the oil, I'm not sure there's a lot of that the oil would just magically kind of go straight into the lagoon. I don't know the modeling of that specific scenario. My point is that I think there are conditions in that environment where you can do a net environmental benefit analysis. Other response options are not only challenged because of the physical environment, but just because of the logistics and the availability of those. If that oil was dispersible and it would have been dispersed near that ship, I think it could have gone in and caused probably significant impacts into the relief in the vicinity of that tanker, but it might have mitigated impacts. I don't know about the shoreline in Mauritius where that oil impacted, but we do know that mangrove forests can be damaged by surface licks quite easily. You choke them off with a surface lick, and then they are dead. They're dying. They're going to die, and there's not much you can do about it. And that is a long-term issue. When the mangrove forests die, it takes decades for them to recover. And so I don't know the details of that environment, but I can envision that if